middle of a derivation. Like, dang it. We were so close, but yet not quite there. So we need to get our brains back into it so that it actually matters and makes sense. So let's take a look here at what was going on. So the game is the thing that we were trying to do last time that we started, was to come up with some sort of explanation for how gases move in some sort of container. Okay? We're trying to describe the motion and how it relates to the temperature, because we know that there is a relationship there, but we're trying to actually give it some sort of formal equation or something like that. Okay? So we had some postulates talking about a large number of molecules, same mass, all moving in random directions, the variety of speeds. They're not playing with each other much, but when they play, they're all collisions, and the collisions are all perfectly elastic. So that was kind of the setup that we had. So we're going to take a little cube of a cubical container, okay, and we put a gas in there, and there's pressure because, well, we figured out why there was pressure, right? Those little particles are moving back and forth, and they bounce into the wall. They bounce into the wall, and they apply a force, right? They apply a force, and that force is over a certain area, and that gives you a pressure, and that's what pressure is. That's where the pressure comes from. And so then we were just using that classical physics stuff that we know and love, like the impulse momentum theorem and the definition of what it means to be an elastic collision, to get us to a statement. Here we said that the force caused by one particle, okay, is going to be equal to its mass times its velocity squared divided by the length of the box. Okay? But this is only really talking about the force in the x direction. Are all of the particles moving back and forth in the x direction? No. Some of them are moving in the y direction, right? Some of them are moving in the z direction, and some of them are moving in not one of those three specific directions, but they've got components in all three of those directions. Does that make sense? So we got all this vector craziness. Now, that may lead you to be going like, oh my gosh, and now we have to break down vectors in 3 dimensions or whatever. But here's the deal. We're talking about a heck of a lot of particles with lots of different speeds, so really we're just going to play the statistics game. Okay? Statistics makes everything nice, so we don't have to look at each little particle, because who wants to do that? Not me. Okay. So here we go. If we talk about the actual force, okay, on a wall, let's see, we're going to do this one wall at a time, okay? It's really, so the force on that wall is not just from one particle, but it's from all of the particles that have some sort of x component, right? So it's going to be the sum of all the forces by all capital N, that was the number of molecules, right? Okay, that are moving in one direction. I'm going to say with the x component, because we're just going to talk about x first. So that's like F is equal to, the mass of each of them is the same, and the length of the box is the same for all of them. So I'm going to pull that M and L out, and it's really like Vx1 squared plus Vx2 squared plus, we could write this forever, but we don't want to, Vxn squared. Is that okay? And we could talk about, instead of each one of those velocities, we could look at an average velocity as well. Okay? It's all good. Vx squared, I'm going to put a line over that. That means average. I don't know if they use that in stat or not, but that's the way that we mark it in stat, like stat max stuff. So this is going to be the average of all of the velocities, the squares of the velocities, excuse me. So that's Vx1 squared plus Vx2 squared plus all of them added together. There's Vxn squared divided by n molecules. Okay. And so if we put these two things together, we can say that the total force is really like m over L times the number of molecules times an average velocity squared in the x direction. And I'm going to put that as F sub x. Is that okay with everybody? And if it's not, then please tell me. Do you need some lead there, my friend? Here. Give the kid a pencil. Right. Logan, give him this pencil. Oh, it's gonna work? Okay. Okay. Oh, I didn't realize that you got it to work. I just don't want a disaster to happen, you know? All right. So that's the x. But we don't just want the x, we want all of it, right? The y and the z too. So
how do you find like Vx1? Do you like measure it?
Sure. I mean, we're talking about this very theoretically, right? We're not actually going to do this physically.
Yeah.
But we're just talking about this theoretical idea of how we can relate that force to the velocity.
Okay.
And then we're going to take it one step further, and then I think it will go, and the clouds will part, and it will be a beautiful thing.
I believe you.
Is that fair?
Yep.
Okay. Yeah. It is a little bit weird, right? Like, okay, I'm going to put a little tag on this one and watch it, and then I'm going to take it. No, we don't do that. That would be a very inefficient approach to all of this. Yeah. So because we have molecules moving in 3D, 3 dimensions of motion, does it make sense, just like if you were breaking up any vector, you're just going to use the Pythagorean theorem to break the vector up? So we can say that the velocity squared, I'm going to just go ahead and do averages, is equal to the x part squared plus the y part squared plus the z part squared. Okay, so that's just like breaking up vectors that we did in 9th grade. Okay, where we're breaking them up into the two pieces. Okay, and we can say this because all the velocities are random. So we really want to just look at averages. And because all the velocities are random, we can also claim that the x stuff, the average in the x, and the average in the y, and the average in the z, oops, that's not a vector hat, that's an average hat, sorry, are all about the same, statistically. So that means that we can say that v squared, the average of v squared, is really like 3 times the average of Vx squared. Is that okay? I'm writing like a lot of crazy stuff on a Thursday morning. Are you feeling okay so far? What's that? Point taken, point taken. And now, well, I'm going to do one more step. The reason that I'm doing this is because I have this thing here, this Vx squared, but I want to put it in terms of the actual velocity, the total velocity. So I'm going to just move this, I'm going to move the 3 to the other side and say that Vx squared could also be written as the average velocity squared of the particle, the total average velocity divided by 3. Life is okay? So the force on one wall, like, oh, I don't know, the x wall that we were looking at, we can write that in terms of the total velocity of the particle. So I'm going to move this down just a little bit here. I'm going to say that F is equal to m over L times n, the number of particles, times the average velocity squared divided by 3. Okay? So just to kind of get this in our brains and make sure that we know what this is the total force on one wall. Oops. Okay. From n molecules
Is it just the one wall, or is it
Let me write the rest of the sentence and then I'll answer your question. Is that fair?
Yeah.
Yeah. So taking into account the three-dimensional motion. Sorry, I have a hard time multitasking in that way. So we're just talking about one wall.
Okay.
Because when we got the M over L stuff, like that L stuff,
Yeah.
we were defining that as it was going this way and then back.
Okay.
Does that make sense?
Yep.
Yeah. Yeah. Good question. All right, so we've got a force. That's the force of all of the particles acting on that wall. Okay? Lots of particles acting on a wall. If you know the force, the total force, and you also happen to know the area of the wall, then you can define the what acting on that wall?
Pressure.
The pressure. Yeah. So the pressure on the wall, we said that pressure was force over area, right? So we're just going to write a whole bunch of stuff. Are you ready? Here we go. So I'm going to, well, let's just do it. So
L's going to cancel out?
well, let's figure this out. So I'm going to write the F stuff here. M over L times N times V, V, not 2, V squared averaged divided by 3. So that's the F. And then we're going to divide that by the area of that wall. And I have to go back and look at my picture just to make sure that I'm all doing this right. What is the area?
L squared.
L squared. So I've got an L squared on the bottom. Now, do the L's cancel out?
No. They don't
No.
stop, but some stuff happens.
But some stuff happens, right? Because you've got an L in the denominator of that top part, and you've got an L squared on the bottom. So that gives you an L cubed, which happens to be the volume of the box. Is that okay? So we can write this then. I'm going to pull that 1/3 out because I can. Because it just makes me feel better to get the constant stuff by itself. Mn, the average velocity squared, divided by the volume. Okay. And because I can, this is that whole like manipulation because it's fun, right? I'm going to multiply by V. So now I've got PV on one side is equal to, well, that's 1/3. I'm just writing this all out here again, times M N V squared average. And is that all okay? Yeah. And I wanted to do one more thing here. Oh. Well, I want to multiply by a half. Can I multiply like by 2/2? Am I allowed to do that? Is that an okay thing? Okay, so I'm going to multiply by a 2/2. So those of you that haven't had me for a while, like, why are you doing that? Because I can, right? Here's why. If I do that, I'm going to have a 2/3. I'm going to have an N. And then I have a 1/2 and an M and a V average squared. And that's interesting. Some people are like, ooh, ah, right? Why is that interesting? That's the kinetic energy, right? Are you with me there? So now we're talking about energy. So we've got something there. So we've got PV is equal to 2/3 N times the kinetic energy of that system. So I'm going to write that down here real quick. Sorry, I'm almost there. Okay. I'm also going to just, because I can, remind myself that PV equals NKT. Remember, that's the big N, the little k. So that's the number of molecules, and that's Boltzmann's constant, not the universal gas constant. Okay. So I'm going to say that this is equal to NKT. Oh, there's an N on both sides. Well, that's cute. So we can relate now the kinetic energy of the gas directly to the temperature. It real. What? So this is really 3/2. Oops, there's no N in there, sorry. 3/2 KT.
Miss Carlin?
Yeah.
The NRT?
It's little n big R, and the little n would be the number of moles, and R is the universal gas constant.
Yeah.
But you can also write it with Boltzmann's constant, which is K,
Uh-huh.
and then you use the big N for the number of molecules. Do you want me to go back and show you that again? I can.
No, I remember what K is.
Yeah, yeah. Yeah, it's just, you can write it either way.
Okay.
It's just that this is the more natural way to do it for this one, because then you get rid of your molecules.
Mm-hmm.
Yeah, yeah. And then we put a big box around that, maybe 2 boxes around that, because that one's important. I think maybe even that one's on your equation sheet. You could check. I'm not positive. I'm not going to swear yet, but I'm pretty sure it's on there. Yeah. It is. Do you see it halfway down, or 2/3 of the way down in the fluid mechanics and thermal physics section? Yeah. Yeah. Okay. So, the moral of that story, as a Physics 2 student, you're not just going to plug in numbers, right? We just need to really think about what that means. It means that the average, because remember this is the average kinetic energy, because we've got that average little deal up there, okay? The average, now they're very specific about this translational kinetic energy. We're not talking about the rotation business. Woo, because we don't want to go there. It doesn't really matter for what we're doing, okay? We'll just say the average kinetic energy, okay, of each molecule, okay, is directly proportional to the temperature. So it's not just something that your chemistry teacher tells you, or that your physics teacher tells you, okay? It for real actually does happen. Okay. One more little thing, because I think it's on here too, and I just, it's better to. Maybe it's not. Never mind. We could find the velocity of any of these given particles as well. And to do that, I'm just gonna write this down because it's nice to know. So 1/2 mv average squared is equal to 3/2 kt. So you can solve for the velocity if you want to know how fast those molecules are going, okay? Because you've taken an average first and then you're going to take the square root. This is where that root mean square thing comes in, RMS. I don't want you to get all freaked out about that, but I'm just going to let you know that that's what it's called. So if you see it, you don't get all upset. Your 2's go away there. And so you can say that this is, 3 kt divided by m. So if you want to know the velocity of any given particle, you can figure it out. Is that okay? Okay. No major complaints, questions, issues? Okay. So I have a problem that I was going to have you work on, but I think it's almost so straightforward that it's not super fun. So this is what I'm going to do instead. I'm just going to let you look at it for a second. Can you find the speed of these molecules? If you know the temperature, we need to convert the temperature to Kelvin. Okay, you know the mass. So you can, does this make sense? One could do this pretty easily. Plug numbers in, push enter, go. Yay, team. Okay, so if you want to do that, go back and watch the video because you'll be able to see the problem. It'll be a beautiful thing. Okay. I want to work on a lab because I want to make sure we have time to do it today. Does that sound okay? Issues or questions about kinetic theory? It's pretty straightforward. I just kind of like it because it's like just watching little balls bounce around in a box. So, all right.